All right, I think it's time to go ahead and get started. I'll do a little round of introductions here. So first of all, my name is Nathaniel Jones, and I'd like to thank you for joining this webinar, Quantifying the Unknown, Non-Destructive Tools for Existing Buildings by Tyler Pillett and Yasser El-Masri. This webinar is hosted by the IBPSA-USA Research Committee with the goal to share new ideas from research to the building simulation community. If you have questions during this webinar, please type them into the chat window. At the end of this 40-minute presentation, I'll unmute our audience on Zoom for a discussion with Tyler and Yasser. AIA Continuing Education credit is available for attending this webinar. Please email info@aiaeb.org with your AIA membership number to receive credit for attending today's event. And now, I'd like to introduce Tyler and Yasser. Go ahead, guys.
Hello, my name's Yasser El-Masri.
Hi, I'm Tyler Pillett. Yasser, can you go back one slide? Just to
of course.
There we go. Yasser, do you want to introduce yourself a little bit further since we're still waiting on some people to join?
Okay, so my name is Yasser El-Masri. I am a PhD in architecture student at the High Performance Building Lab at Georgia Tech. Currently doing my research on retrofits and non-destructive testing techniques, and even simulation tools that work in tandem with all of those. Ty? Yeah.
And I'm Tyler Pillett. So much like Yasser, I'm also a PhD student in the High Performance Building Group at Georgia Tech, specifically a PhD in architecture. So my research is actually very similar along the lines of Yasser. I guess we both had some good ideas starting out. So my research is also about non-destructive testing and understanding what building envelopes are made out of without actually having to tear them apart.
Yeah. Daniel, shall we start with the presentation or should we wait just a bit more?
I think it's a good time to go ahead and get started.
Okay. So today, this is going to be a quite unorthodox kind of webinar that you're seeing. Me and Tyler, when we wanted to find a format to do this, two people doing a webinar, we wanted to play on the strength of having both of us. Me and Tyler are good friends. We're already colleagues. So we thought, why not give people a bit of a treat and have them get the most fun credits for the AIA that they've ever had. So we actually are introducing the first Jeopardy HPBL IBPSA-USA webinar edition with your two handsome hosts, which you just had met. This is me and Tyler. We're both, as we said, PhD students at the Georgia Tech High Performance Building Lab. And today, as your hosts, we're going to be introducing the panels ahead. So if you're not familiar with Jeopardy, Jeopardy is a very popular TV game show in the United States. Effectively, there are different categories where the contestant would select a category and a dollar value number for it. The question would come up and they would answer. Whoever answers correctly gets the points. Definitely, we are playing a modified kind of Jeopardy today, so we will go in a bit of a sequence. But the fun thing is, me and Tyler have prepared questions for each other that we're not entirely familiar with. So we're going to need your help through the chat box on the right. When we see a prompt and answer on the question on the screen, we want you to help us out in the chat screen so we're able to find those right answers. We're not really keeping any tally or score, but this is just for the fun of it. But we hope you kind of enjoy it. And Tyler's going to just take us through the categories that we have today, just so you have a small idea about what we're going to do.
Yeah, and much as Yasser said, I just want to reiterate, please, 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 answer in the chat box on the right whenever you have just any idea for the question, because this is all about you guys helping us out, since we really don't know some of the answers to these questions. Since this is something that the both of us really haven't seen each other's slides, to be honest. So the categories for this entire Jeopardy round are as follows. Starting out, we have Just Another Brick in the Wall, which is talking a little bit about building envelopes and getting a little bit more information out there so you understand why we care so much about envelopes. And then we have Chug, 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 which is kind of a play on the building drinking up all that energy, really, wasting a lot of energy. And it's all about statistics and all about information about our built environment and how we can make it better.
And feel free to get those wrong, because you're going to have to guess like we are.
Yeah, and then after the building's done chug, chug, chugging, then we have the building AA, which is the how we can kind of solve some of these problems and try to mitigate some of these issues that we talk about in the previous section. And once again, this is all about statistics and all about just understanding how we can address the problem. And then we have NDTs, please, which is related to Yasser's research. It's all about different non-destructive testing tools that you can use to learn more about your building. And then moving forward, we have the heat transfer warm-up, which is the beginnings of my research, since my research is all focused on heat transfer. And this is just a lot of basic heat transfer and a little bit of basic building science, just so that we're all on the same page. And then the last section is let's get characterizing, which is all about my research, and it's all about thermal characterization and understanding what things are made of. So I guess we can maybe go ahead and get started.
Yep, we can get started on that one. So for the first category, I prepared questions for Tyler and everyone in the audience. Let's get this starting. So Tyler, for 200, just another brick in the wall.
All right, let's do it.
So it is a dynamic microcosm of thermal, chemical, biological, and physical processes. Tyler and the audience, go ahead.
Yeah, I'm definitely gonna need some audience assistance on this one. Yeah. So, man, this is actually a little tricky. I don't quite know what this could be, because this kind of sounds like human body. Yeah. This could also be like the environment.
Yep.
Man, the thermal, chemical, biological, and physical processes. That's
well, take a hint from the theme. That's just another brick in the wall.
Oh, I see. I guess I'll go ahead and say maybe building envelopes.
Building envelopes.
Doesn't seem like we have any takers in the chat, so I'm just gonna have to go with that.
You guys you need to help us out on this one. But effectively, that would be the building wall. So you are correct, Tyler. And it is very interesting that you would say like something like the human body or the environment, because you know, here's a picture of a brick wall, which is which is almost used as a euphemism for something static. But through our research, we always find out that, you know, walls are almost inherently very dynamic. There's a lot of processes happening in there, and that's why they're some of the most interesting things, even if it's, you know, stiff as a brick wall. So let's go for 400 and just another brick in the wall. So this percentage of energy use in buildings is a result of thermal losses through the envelope. Take a guess. Percentages and all that. Just take a guess.
I'm not really sure. See, do we have any takers in the chat? Anybody have any guesses as to what this could be?
Tyler definitely needs your help on this one.
I feel like it's maybe 30%, 40%. Okay.
40%.
Okay,
yeah,
40.
We have a 40%. Do you want to take the 40%, Tyler?
Give it one more second. I mean, 40% sounds a little bit better, because now that I'm thinking about 30%.
Okay.
Depends on the envelope. That's true. I'm gonna go ahead and say 40%. Let's go with that one.
Let's go. And that was actually for Jay Smith, you got very close. So that's around 42% according to the DOE. So a lot. You can see that, you know, it's almost half of the energy loss is going to happen through the envelopes. Let's go to 600. You're getting good help, Tyler. So you're going to do well. Is that an average in the USA? I guess so, according to the DOE report.
Yeah, I believe it is an average.
We can definitely share the sources that we have. They're always down in the bottom for everyone that wants to check them, and we can share that afterwards. So for 600, when measured accurately, it yields differing results at each individual second of the day. Follow the theme, Tyler.
Yeah, let's see. This could, once again, like the first question, it could be a lot of things. This wind measured, I mean, this could be like outdoor temperature, solar gain. That's what I was solar gain changes throughout the day. Outdoor temperature does. I'm gonna go ahead and say solar gain. I mean,
okay,
help me out here.
Solar. So we have Jay Smith, solar radiation and direct. Effectively, I think all of you are correct, because it's really building envelope performance. So Scott is celebrating with us. You can see that celebrate. It is correct. All of these things are related to building envelope performance, and it's super important for us to understand that at every individual time step when measured, you're going to see a different result. We cannot look at them as very static objects. No, envelopes are very dynamic by nature. We're doing really good on this category, Tyler, and you're getting some good help. So let's go to just another brick in the wall for 800. It ideally keeps the outside out and the inside in.
Ideally keeps the outside out and the inside in. I feel like this could definitely be weather barriers. I was thinking a little broader, just the envelope itself, because shoot, a weather barrier is just for water and stuff.
Okay.
Yeah, so
we have
seeing a lot of things in the chat box here, but I believe those are for the previous questions.
Yes, those are previous questions. So weather barrier, do you want to go with that one?
I think I'll make it a little bit broader. Let's go for envelope.
And actually, it is a good building envelope. This is just something we need to understand, that a good building envelope, and there's no particular shape or form for that. It can really vary, but a good building envelope is going to keep the outside out and the inside in. It's really what it is for. So
that's true. That is true. It does not include windows, so we need to be a little bit broader.
And we have people from YouTube as well saying air vapor barrier, which can be part of a good building envelope. So everyone's correct so far. Let's do just another brick on the wall for 1,000.
All right.
Okay. So a good building envelope can help combat this international problem.
Well, we got a lot of international problems to deal with. With building envelopes, that's pretty localized. It's pretty small scale.
Yeah. But when compounding the effects of having just a bunch of really good envelopes, what international global problem do you think it could really start combating and helping us fight?
I'm thinking climate change. I'm not seeing too many takers in the chat, but climate change is probably my guess.
Yes. Okay. Well, I mean, I guess global warming.
Yeah, we're on the same track.
Indoor thermal comfort as well.
That's true.
It's actually climate change. So you got it right on the head, Tyler. Effectively, having good building envelopes all over the world on a combined effect can really be helping us tackle climate change on a big level. And in the next category, we're going to start delving deeper into why a good building envelope effectively can help you tackle something as big as climate change. We actually, because there's a bit of delay between YouTube and here, we got people actually saying climate change as well. So kudos to you, and people are getting it correctly. So let's go to chug. Effectively, buildings are chugging in that energy. So let's look into that. For 200, Tyler, 50% of the U.S. commercial building stock was constructed prior to this year. Take a guess. Just take a guess.
Prior to this year. So the U.S. specifically.
We got a 1960.
I was thinking 1960. I was thinking maybe 1970.
Okay.
1960 kind of seems a little bit more reasonable to me, though.
Okay.
Now that I'm really thinking about all the buildings I see around me in Atlanta.
Okay, we got a 1940 as well.
We're getting older.
We're getting older. Yep. Well, let's just wait for a couple more seconds, see if you can get any more help on this one, because this is effectively a tricky question, because the numbers vary sometimes from source to source, and at the same time between residential and, in our case here, commercial buildings. Okay, and Scott, we got a 1970, a 60-year life. Yep.
1950. Yeah, we're getting a lot
effectively a lot of baby boomers. Right? Just let's get that in there. Just that kind of era. So let's look at the actual. It's actually 1980, and just to clarify, the number is definitely debatable. This is from the EIA and the commercial buildings saying that, but people had said 1970. It's a very well touted kind of number, but that would generally be more for residential buildings as well. But 1980 is really the stock. So 50% of all commercial buildings in the United States have been built prior to 1980.
I see.
Okay. Let's go to 400 for chug.
All right, let's do it.
Only this percentage of existing buildings are renovated annually. This is a tough one, Tyler, but let's see.
So you said 1980. 1980 is 50% of our buildings were built prior to then. So man, I'm thinking that buildings, maybe we're not renovating that much. Okay. It seems like we're building. I don't know. I'm trying to think through
8%.
This. 20. I was thinking maybe 10.
Okay.
10 seems. I don't know. I mean, 20. I personally have not done that much with retrofits. I know we talk about it a lot, but I just don't see them that often. I'm feeling like 20 might be a little high.
Yeah, but we got, Scott saying 8. Do you kind of concur with Scott on 8, or?
I'm thinking maybe like 8 to 10, something like that.
Okay, okay.
Oop,
2.
We got 2.
Ooh, we got a 2. Someone is pretty pessimistic about, renovations. You take stab. Okay, yep, Scott, you take stab in the dark, and that's exactly what we are doing. So you're doing the right thing. 5%. So we're getting lower. Let's actually see what it is at this point. It's actually 0.5 to 1% only of annually, buildings being renovated annually. It is very low, and that kind of really opens up. So we got a boo from John Smith. Exactly, boo. We're doing a very bad job on retrofits, keeping up with code. Trying to get those envelopes specifically, if we're talking about that, up to standard. So yep, we got a less than 1% for sure. So whoever got that from YouTube, I know there's a delay, but kudos to you. You got the right one. So let's go for 600 on chug, chug, chug. So buildings consume this percentage of total electricity generation in the US.
I'm trying to think of things that I've seen before.
We got a 70 from Scott?
Huh. Yeah, I've seen 2/3 for sure somewhere. I don't remember when.
Pretty close to Scott's 70%. So, a lion's
Scott
share.
and I seem to be on the same page here.
Yeah. 74%, Stefan. Okay. Let's give a couple more seconds to see. But I think, everyone here is going into the same kind of range, effectively, into what? Okay, we got a 40%. Like so I'm going to say to Dan, this is not energy. This is electricity, because I will tell you that 40% of energy is used by buildings, but we're talking about electricity specifically. So let's go to the answer. It's actually 76%. So 76? Everyone that said,
we had a 74.
We got a 74.
We were close.
So we were close. Exactly. 76% of all electricity in the United States is effectively going to actually going to buildings and building consumption. Whoops. Let's go back to that one. So for 800 on chug, 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 buildings emit this many tons of CO2 yearly. This is a tougher one for people doing building science out there, because generally we look at kilowatt hours and a lot of energy, but we're not really looking at the carbon emissions. So take a guess on this one. It's a tough one, but it's good to know.
This many tons. I don't even know. I don't even know where to begin.
Okay.
Do we have can we get a hint on maybe like?
So let me give you something.
10 to the 9th, or like what are we talking
so we
about
are really looking at gigatons, which is definitely 10 to the 9th. So we have a lot, and that metric alone is going to tell you how bad in terms of climate change, buildings are doing. So I know it's a tough one. That's why we're not seeing a lot of people on it. But let me actually give you the number on that one, and that's actually 9.7 gigatons, which is a massive number.
It's a big number.
It is definitely a big number, just so we know how big of a problem we have and why actually me and Tyler are actually in this business, and what we're actually trying to do through our research. So for 1,000 on chug, chug, chug.
All right, let's do it.
Buildings in OECD countries being the Organization of Economic Cooperation and Development, so effectively developed countries have an organization, consume this percentage more BTU per capita than those in non-OECD countries, which here are a stand-in for developing countries. How much more does a building in a developed country effectively use more per capita than in a non-developed country or a developing country?
So we're talking about energy here.
Yes, BTU. We're talking about BTU per capita.
Maybe 50%.
50% more. Okay, we got Scott. Scott's going with you on the 50% more.
Yep, Scott and I are always on the same page.
Yep. Jonathan. Oh, okay. He's gone for 200%. Okay.
That's pretty big.
That's a pretty big number. Yep.
I'm trying to really wrap my head around it. Maybe Jonathan's onto something. 200%. Because actually, when I was thinking of 50, I was thinking of 150 times. Yeah, I was thinking of 1.5 times actually. Now that I'm thinking about it.
Okay.
So maybe 200.
So let's see. The actual number is actually 560% more per capita BTU used per building in a developed country versus a developed country. And when we look at the EIA numbers on this one, we can see how specifically on the right, we can see like this trend is not even changing. Both are kind of slightly increasing, but up to 2050, according to the EIA, this difference is going to stay the same. So we really have a big problem. This isn't just about, industrializing countries now coming in. No, this is about energy use in buildings in developed countries like the United States. So there is an issue that we have a lot on the home front.
We're not even retrofitting.
We're not even retrofitting.
How are we even going to attack that?
Yeah, exactly. So that's why that, this kind of stunning metric kind of shows you that there's a lot to do on the home front for looking at, developing countries and blaming their industrialization on. So now that we've gone to both of these, let's go to the building AA.
All righty, I'll go ahead and take over then.
Yeah.
So I guess let's go ahead and do, let's start with building AA for 200.
Okay.
All right, so yes, sir.
Yeah.
So this ASHRAE standard establishes consistent practices for conducting and reporting energy audits for commercial buildings.
Yeah.
What do you think?
ASHRAE standard for reporting energy audits for commercial buildings. Yep. That would be actually, I believe, standard 211P, if I remember that correctly. I would say that.
All right. We don't have too many takers in the chat, so let's see what it is.
That's actually ASHRAE standard 211. Yep.
Looks like Yasser knows a little bit too much here.
Yeah. So let's do building A for 400 tile.
All right. So as we talked about 211P, ASHRAE standard 211P specifies the building and element as the main contributor of energy loss.
That one. So there are many contributors to energy loss, really, when we were looking at, a building. But I think going off what we kind of talked about before, I believe, HVAC is something in there. Scott's saying envelope, Windows, envelope, thermal vigilance, and HVAC. Sure, I think actually it's really all of them in a way. I think it's really all of them in a way. But yeah, I think, going off like 42% that we said kind of going through the envelope, I'm going to actually stick with Scott. And, effectively thermal bridges and windows are really the same. They're part of the envelope. So I think everyone's on the same way. Shall we reveal the answer?
Let's reveal it.
That is the building envelope. Yep. Oh, we got another window.
So windows, yep. Yeah. I mean, everybody's all on the same page. Yep. The envelope's a big problem. Yeah.
So effectively, yep, the building envelope, a lot of things like thermal bridges, as we said, cracks, even, and moisture, a lot of things happening in there. A lot of them can have energy loss going through them and actually compounding and increasing. Glazing as well. So it's kind of all around the same kind of thing.
Yeah, leakages. Okay, cool. It's all on the same path.
Awesome.
We need to think about envelopes.
Okay. So let's do building A for 600.
Let's do it. All right. So yes, sir. Used in inspecting the envelope, these techniques drive down labor costs, repair costs, and are safer than traditional methods.
Okay. These techniques drive down labor and repair, safer traditional methods. I definitely say what you're referring to. Let me see. Let's see if there are any takers on this one, because I have a pretty good guess on that.
Yeah,
envelope commissioning.
Man, that sounds good.
That sounds like a good one. Infrared thermal mapping. Okay. I definitely see a kind of a pattern here. Effectively, I would say that, what infrared thermal mapping, but you're talking about the actual, like these techniques themselves. I'd say we're talking about something like non-destructive techniques, NDTs.
Yeah, I think so. Let's see.
Yep, non-destructive testing techniques, NDTs, which infrared thermal mapping is definitely a part of, and envelope commissioning uses NDTs, I guess, the same kind of thing. Let's do the building AA for 800.
All righty. Let's see. So these devices can carry non-destructive testing equipment around the building without limitations.
Okay. So are we talking about like height limitations, Tyler?
Say that one more time. Did you say height?
Yes. Are we talking about height limitations?
Yeah, I think that we do need to be talking about height, because there's a lot of limitations you could think about. I mean, we could be saying weight.
Mm-hmm. Okay. There's robotics and there's drones. I'm going to go with Carlos Velasquez on this one, because effectively, I guess so. Scott thought he saw a drone on the previous slide, but I don't think
that could be it.
That could be it.
People are a good answer, but we don't like to refer to them as devices.
Okay, shall we reveal the answer, Tyler?
Yeah, let's do it.
Effectively, unmanned aerial vehicles, UAV drones. So I guess, we got a lot of good takers on this one. And yep, it is drones. So whoever said drones, thank you for helping us out on that one.
All right. Yes, sir. So I'll let you go ahead and read the questions for the next section, and I'll go ahead and answer it for you.
So for NDTs, please, let's go with that one. For 200,
let's do it.
For 200, Tyler, seeing a different spectrum, this NDT can measure thermal properties of envelopes, detect moisture, invisible physical defects, and can be carried on a drone. What non-destructive testing technique can be, sees a different spectrum and can see a lot of this stuff? So thermal properties.
Sees a lot of different stuff. Invisible physical defects, carried on a drone, so it's probably light.
Okay, it is. It can be light.
Measure thermal properties. I'm seeing it in the chat, and this is exactly what I was thinking. I'm thinking this is probably thermal imagery or thermography.
Infrared thermography, infrared thermal. You want to go with that one?
Yeah, I think so. I mean, we're seeing some people in the chat that are agreeing with me on that.
So it effectively is infrared thermography, infrared thermal mapping. It's all kind of correct. It really does, when you're looking in a different spectrum, you can see a lot more about the dynamism of the building that we were talking about, the envelope. And this is what, in general, all the NDTs that we're going to be looking at are going to help us see the dynamism that you don't really see from the outside. So you got some good help on that one. Let's do NDTs, please, for 400.
All right, let's do it.
These two techniques are based on ultra-wideband and Wi-Fi radio waves. They can measure material depth, detect material composition, and possibly be carried on drones. This is a bit of a tough one, I have to say, but just think of any kind of, testing techniques or equipment that's definitely used in like surveying buildings that uses Wi-Fi radio waves or ultra-wideband radars.
Yeah.
Okay, we got someone saying laser mapping.
Trying to think, because I know I've been told about research that's out there trying to detect moisture with radio waves. Yeah, I'm thinking radar.
So Scott says radar, and generally you and Scott are in consensus, Tyler. So do you want to go with Scott?
I'm not sure. I feel like we're maybe not specific enough, because you use specific words like ultra wideband and Wi-Fi. So
yeah, but because this is a tough one, I'm gonna let you could generally kind of talk about a general kind of NDT.
Yeah, so I think Scott's got it. I think let's go with the radar.
Let's go with radar. Effectively, yep. These are ultrasound and through-wall imaging radar. These are NDTs that can definitely be used to, you emit a particular wave into a structure, and through time of flight measurement or different kinds of measurements, you can measure distances, identify if things are happening there. And, through-wall imaging radar can even look beyond the wall and things inside, the room itself. So both are very interesting, and they can provide a lot of insight, on what's happening within the wall and beyond it. So Scott, on the money. Let's do NDTs, please, for 600. So they actually are not the exact same device, Scott, just to kind of tell you on that one. They use different waves. So you can use the TWIR through-wall imaging radar using Wi-Fi radio signals, and the ultra-wideband radars can be used with ultrasound, and which are shorter in wavelength. We can definitely, in the questions, discuss it even more. So 600 for NDTs, please. Using digital photography to take images of an object from all angles, it can extract the features of a building envelope, detect and model cracks, and can be effectively carried on a drone. Simple digital photography.
Oh, digital photography. Yeah, because when you said carried on a drone, I started to think that we were talking about like LiDAR or something like that. But you say digital photography.
Yeah. Any takers? So you take an image, take a lot of images of the same object, effectively, from different angles, and you can start extracting features. So someone's saying pictometry. So pictometry.
I don't know what that means. So maybe they're right.
But I'll say someone's onto something. So
yeah, it sounds like they know a specific term that I'm not aware of. So maybe they know what it is.
Facial recognition for you. Okay, someone says photogrammetry.
Okay, it seems like a lot of people in the chat know what they're talking about compared to me with this one.
Okay, so it's actually close range photogrammetry. That is correct. Close range photogrammetry, when taking, for example, this is actually thermal close range photogrammetry. When taking a lot of images, you can be creating a model of your building, and at the same time, when taking it from different angles, you could be modeling a lot of cracks and different things that are happening, plus extract different surfaces, so windows, doors, and we're getting some late people saying photogrammetry as well. So on the money. Doing well on NDT species. You're going to get a lot of good help. I thought this was a pretty tough one. Yep.
Yeah, so you said that you could see cracks. They can be that detailed?
They can be that detailed. So if taken pretty close and, using a machine learning algorithm, there's a lot of research out there, they can actually effectively detect when you're stitching the images together on the facade, you can actually detect where there are issues or not. Another researcher in the HPBL, Dr. Kaiwan Chen, which was a postdoc now, had conducted research regarding this and actually was able to extract cracks on buildings using photogrammetry as well. So let's do $800 for NDTs, please. Emitting a laser beam to measure reflected light from surfaces, this NDT can extract envelope features, detect physical defects, and can be carried on a drone.
All right. So for the last one, I said LiDAR. And this sounds a little bit more like LiDAR to me.
Yeah. Okay. Yeah. Well, that's definitely a good guess.
Are there any guesses in the chat?
Effectively, a laser beam. I think someone before on the last. Someone's saying LiDAR. I think Hobbs said laser mapping in a previous NDT, but she might have, thought it's the same along your lines. So, LiDAR and laser scanning are similar in a way. So laser mapping.
Yeah, we got a lot of people agreeing on that.
So do you want to go with that one, Tyler?
Yeah, I think that's definitely it.
Okay, that's actually LiDAR, but laser scanning as well works for laser mapping. They use the same kind of equipment, which is you're emitting a laser. The only difference is how they do the measurements, which is a time of flight measurements versus another way to do the measurement. But both are actually good answers, and you guys are on the money. I really thought this was going to be harder, but you're getting a lot of good help on this one, Tyler, today. So let's do NDTs, please, for 1,000.
All right, let's do it.
Utilizing electromagnetic waves to penetrate deep into surfaces, it can measure material depth, material composition, detect moisture, identify physical defects, and can be carried on a drone.
Man,
so take a hint, which is to penetrate deep into surfaces.
Yeah, so it penetrates through the surface, measures depth, composition, moisture, and this is different than the ultrasounds and Wi-Fi that we were talking about, because those are electromagnetic waves too.
They are, but this one has way more depth into when you're looking into a particular object. So it is close. It is close. It's definitely a closer kind of at the same family. But let's see if something that can look deep into the surfaces. And I'll give you a hint for that one. It's generally used for both looking into the ground and into structures and buildings.
I'm not sure.
Any takers? That's a tough one. That's why it's $1,000 question.
Yeah, extra.
Yeah, see?
So that's what it sounds like you're describing.
That's not actually too difficult. So scanner, okay. Let's see if one more taker, if anyone wants to. Nut thumper trucks. Okay. So I think let's reveal that, since this is a tough one, but today you'd have learned something, which is,
I'm not sure.
It's actually ground penetrating radar. So you are correct to say that it is similar. As I said, it's within the same family, but ground penetrating radar is actually used to look into very deep things, such as, finding things within the ground. Archaeologists use it, but at the same time, people in the construction business use it to identify if there's any kind of object within the structure itself. So it is radar based as well, but it has a lot of depth into how you look.
I see.
Okay,
we did miss one, so let's go back.
Yeah. So yes. So for the final one for the building AA, let's do it for 1,000. Let's see. So this is actually built of researchers at Georgia Tech, aka me, working with my advisor, Dr. Tariq Raka. We found that by identifying these things, the user can have a cohesive insight into the building envelope through everything that ASHRAE standard 211P has for an envelope. It really follows a theme. So what exactly can we identify to be able to see a cohesive insight? because we saw all the entities before see different things, or like, you know, sometimes they overlap, sometimes they do not. So take a moment to think of that.
Yeah, I'm thinking about what we've seen so far, and I know you talked about thermal imaging, like photo stitching. What is it? Photogrammetry. Yeah, integrated process. I'm feeling like the thermal imaging tells you something that the others may not.
Okay,
so maybe we need to like stitch the workflows.
Wow, someone's saying layers of envelopes. Someone's saying aggregating data from all entities. So, you have a taker?
Yeah, I think that so see integrated processes in aggregating data from NDTs. So I feel like that's it. Like the different NDTs tell you something different than each other.
And that is actually correct. Hybrid NDT workflow. So people saying aggregating data from all NDTs, integrated process, that's correct. Through our research on the HGBL, we've identified and actually surveyed different NDTs and on the actual categories we've identified that are relevant to the ASHRAE 211P. We've kind of looked through the literature and identified relevant literature that kind of shows that, you know, the NDT has been used in this application or not, can be carried on a drone or not, or if there's indirect relevant literature, which is a similar application. As we saw, some of these NDTs are actually pretty similar in the same family. And effectively using literature tools like this, you can actually start creating hybrid flows. So you would effectively, if you want to look at the whole thing, you can be creating something using GPR, which covers these, infrared thermography with those. And, you know, you would need something for this one, which, for example, only thermography would do. So by knowing exactly what you want to see in the envelope and looking at, you know, what NDTs do it, you can create hybrid NDT workflows to do that.
I see.
And with that, I'm going to turn that over to you, Tyler.
All right, so we're getting back into my domain. So I'm going to start out with heat transfer warm-up, and I guess, yes, sir, let's start for 200. Is that
Let's do 200.
All right. So, yes, sir, this metric describes how insulating a material is, and there are multiple right answers for this one. So
okay,
feel free to guess.
Insulating a material is. Okay. I would, yes, Scott, you can. We'll link you the paper that we have actually worked with on and published. It's actually published journal. So I'm going to U-value thermal conductivity. Exactly.
Thermal conductivity.
I'm going to say R value there. That's kind of my U-value, R value thermal conductivity.
All right, let's see. We're getting a lot of similar answers.
Okay, there we go.
Yep, we got R value, thermal resistance, or thermal conductivity. So all of these things, they're pretty much all saying the same thing. It's all about conductive heat transfer and how insulating something is. Specifically, you know, in the built environment, we talk about how insulating our envelopes are.
Awesome. Let's do 400 for heat transfer.
Let's do it. So this is different than the last one. So this metric describes a material's ability to store heat. And this metric is not R value. It's completely different.
To store heat. Oh, okay. So this isn't like resisting heat, which, you know, effectively.
No, it's not insulating. It's like heat storage.
I'd say thermal capacitance, because there's a capacity to store heat. That's kind of my, if that's okay, capacitance. So
we've seen capacitance in the chat.
Emissivity, we got someone saying emissivity. Okay. Let's see if there's anyone else, but I think thermal capacitance kind of is what I'm going
for. And very similar to the last one, there's a lot of right answers.
So let's see.
All right, let's do it.
Oh, okay. Thermal mass
as well. Somebody just said it right on the money. It's almost it's on the slide. So we got thermal mass, thermal capacitance. Some people may say thermal inertia.
Yeah.
Or we have specific heat capacity. So all of these terms are measuring how much heat can be stored inside of something. And when we're talking about a building envelope, sometimes you got to think about how much heat is stored in your building envelope over time.
Okay, and we got a couple of latent answers here that actually have got it correctly. So, all right, not bad. This is a good category. I want to do 600 for heat transfer warm. Tyler.
Okay. So yes, sir.
Yes.
This type of heat transfer assumes that heat only travels in one direction, and this has nothing to do with the band.
Okay, okay. Yes, not one direction, the band. Oh, that was my first guess. So for my second guess, I would say it only moves in one direction. So, you know, we're talking about movement. I would say maybe one-dimensional heat transfer?
Maybe.
I would guess.
Any takers?
Anyone want to help me out on this one? Because I think according to direction, I would do one-dimensional. Linear heat transfer. Okay.
Maybe so.
Okay. Well, I mean,
yes, sir. It's up to you. Do you think that you trust your answer enough?
Okay, conduction. Because like I got confirmation from linear heat transfer. So I think I'm gonna go with one-dimensional linear heat transfer.
All right, let's see the answer.
Yep.
So the answer is one-dimensional heat transfer. Heat transfer is complex. It happens in 3 dimensions.
Wow.
And there's a lot happening to our building envelopes. I mean, specifically in this picture.
Yeah, that seems like a lot, actually.
Walls look boring, but when you think about all of these, conflicting variables and all this stuff happening all at once, it's sometimes a good assumption just to look at things in 1 dimension, just to simplify it a bit.
We have someone that said one-dimensional conductive. I think we'll take that because this is Leighton from YouTube. Okay, so okay, thank you everyone for helping me out on this one. I want to do 800 for heat transfer warm-up. All
right, so this is different than the last one, even though it looks similar. So this type of conduction is characterized by a material taking time to heat up and cool down. And once again, there's multiple right answers to this, so feel free to throw some out.
Yeah, I can think of a couple of things. By a material taking time to heat up and cool down. This type of conduction. Yeah, thermal lag. I'm actually thinking something that has to do with like latency of some sort, which is thermal lag.
The example I like to give is think about a cast iron pan. It takes a long time to heat up and it takes a long time to cool down when you turn the stove off.
Yep. But you're asking about a type of conduction. Okay.
It is a specific type of conduction.
Well,
some call it a regime of conduction, depending on what your background is.
Okay, regimes of conduction. Well, I actually am gonna go with Jonathan on this one and just say thermal lag, although I know it's not the type of conduction you're referring to, but
I see lag in there, so I'll say maybe time dependent. So let's see the answer. So we're talking about unsteady or transient conduction. Jonathan's answer is pretty close. Transient and lag, those words are very much related.
Exactly. So just to understand unsteady conduction, it effectively means, can you give us just a bit of a...
So these are regimes of the heat transfer scenario that we're dealing with, where things are taking their time to heat up and cool down, and it's where thermal mass really plays a lot into how much energy is transferred into and out of something. And when we're thinking about our building envelopes, I mean, we really got to think about thermal mass because we're pretty much always in a transient regime.
Yep. That sounds pretty complicated, I have to say. But let's look at heat transfer warm-up at 1,000.
All right.
Researchers from Georgia Tech.
Yes, sir. Yep. You're the one that's got to answer this one.
Oh, okay. Yeah. Oh, yes. Sorry.
Sorry to cut you off there.
Yeah.
So yes, sir. Researchers from Georgia Tech, i.e. me and my advisor, Tara Crocker, found that this electrical grid scale problem cannot be accurately simulated if thermal mass is not accounted for in building energy models.
This is an electrical grid scale problem.
Electrical grid scale. So utilities care a lot about it.
Okay. And if thermal mass, so we're just talking about, unsteady state, so the latent effects of what's happening, Okay. So I think this is definitely, since we're talking about thermal mass simulation and unsteady, it's a time-related problem, at least on a grid scale. That's kind of how I'm thinking. Someone is saying macrogrid, and I would say, this has to have to do with something with macrogrids. But my guess would be how much consumption is happening at every single hour, because if we factor in kind of the lag, then it can be different than if you're thinking about it, not adding. That's kind of my guess, which is probably hourly grid consumption, something like that.
So distributed grid issues. These are we're getting there.
We're getting there.
I guess yes, sir. Are you confident in your answer?
I'm confident, no, but I would definitely say that, it's the closest I can think from say peak.
Peak.
Oh, okay. Peak. Well, yeah, sure. Peak is like, you know, an hourly kind of thing. Yeah, I can go with peak. Peak
right.
Nelson, peak demand, Joe. So maybe we should,
let's see the answer.
Our YouTube people are getting stuff in. Yep, peak demand.
Peak demand. So can we go to the next slide?
Yes, we can.
So it is extremely important to think about thermal mass when we're talking about peak demand. Specifically here, this is a case where we're thinking about thermal mass a lot, but could you click once more?
Yep.
And when we completely ignore thermal mass, essentially the peak demand that we're seeing in the peak thermal loads are just way off. The peaks are way lower than they actually are, and they're just off by hours. So it's extremely important when we think about building envelopes to actually model thermal mass, rather than assuming things are just a massless R value.
Yeah, but that is a big difference. Wow, okay.
It is a big difference. It's really important. Unfortunately, some aspects of this figure didn't show through. I guess it's just due to the translation, but it's a really big difference, and it's really important that we think about this problem.
And Tyler, the difference in the peaks here is really the effect of the lag, correct?
Yeah, it's an effect of how long it takes for that heat transfer to make it through the envelope.
Okay.
And when we just think that it goes through immediately, I mean, we're way off whenever we're thinking about HVAC loads and so forth.
Yeah. Well, let's do the last category. Let's get characterized for 200.
Let's do it for 200. So yes, sir. This is a test. It's a type of test that measures an in-service envelope's ability to resist heat flow.
So a test that resists heat flow.
Not like school. It's a little different than when you get in college.
I'd say definitely something that has to do with the heat flux, resistance, R value. Maybe some type of test that uses a heat flux meter to look at R value. I assume. I don't know if there's
could be along the lines.
Okay. Yeah, I definitely say like a heat flux test or a heat flow test or a heat flow resistance test. I don't know. They could be a lot of stuff. Scott's saying IR imaging.
Maybe you could probably find it from. I will say that if you use IR, maybe you could you could conduct this type of test. Okay.
Let's see if there's anyone coming in from YouTube that can help us. Maybe some of that lag, some of that unsteady answers coming in.
Maybe some of that. The transient regime with our.
We're still on the transient regime of answers coming up. Thermal couplings by Jonathan. I'm thinking along those lines, something like that. I'm gonna go with heat flow resistance test.
All right, let's see the answer.
So
we're talking about an R value test.
It's an R value test. Okay.
Yeah, so we need to test for that R value, but there's also a lot more going on. So don't get too comfortable once you know the R value.
Okay. Let's get characterizing 400.
All right. So ASTM 1046 states that these two quantities, these two variables must be measured to characterize an envelope's conductive performance. And this is talking about R value tests specifically. Yeah,
so I would definitely, the first quantity would be, I don't know, because R value isn't really a quantity, is it? I don't know, like, is it?
R value is a metric that you derive from
yes, that's what I'm saying, yeah. Like I'd say then thermal conductivity is one thing that, or how much of it is going through.
Let me think of, let's think more along the lines of things we can measure directly with a tool.
So I'm going to say heat flow. Heat flow is one thing. Density by Ben saying density.
Density, you technically could measure it, but that'd be difficult.
Okay, temperature differential and thickness. Yeah, I think temperature differential and like heat flow could be two stuff. Surface temperature, specific density.
Yeah.
Okay, we got a lot.
These are all along the lines. I think everybody's getting there. So
go R value, thermal mass, solar temperature. Okay. K value.
Cool. Yeah, we're all getting there. All right. Let's see the answer.
Let's see the answer. Okay.
So the two things that you really need to measure if you're trying to run an R value test are heat flux and temperature.
Okay.
You can derive R value from these two metrics, but also if you get really crafty with your modeling, you can also derive thermal mass and you can also figure out specific heat and density if you really try hard.
Okay, that's pretty cool. Let's look at 600. So
So yes, sir. This type of modeling is used to calculate input parameters that match a simulation model to measured data. And there's a bunch of different answers here. Sometimes the building simulation community calls it something different.
Okay. This type of model.
Scott asked a question, how is heat flux measured? And that's for the previous one. You can measure that with a heat flux transducer, which uses a thermopile. Those things are a bit of a pain to use, but you can do it.
I was going to say calibrated, a calibration model, maybe something like a calibration model to calculate the input parameters to match the simulation. So we're kind of looking at it in reverse, right? Like we're looking at the process.
Yeah,
we have the answers and we're trying to find the inputs, right?
Yes.
Reverse modeling, reverse calibration modeling, something along those lines.
I think that you're definitely getting there. So let's see the answer because we got some good answers in the chat.
Okay.
We got inverse models, inverse problems, or model calibration. So the building simulation community likes to talk about calibration a lot, but the broader term to describe it is inverse modeling or the inverse problem, where you're trying to find the input parameters to a model that result in a simulation output that matches the reality you're actually measuring.
Awesome. Okay, so effectively we have the data and we're trying to find what inputs have come here. So we're doing the reverse kind of process. Okay.
You can match that with you know, an optimization model, kind of like nonlinear least squares is another thing that people do.
Okay. Yeah, and I think Jonathan even said regression analysis, which I guess is
it's very much along the same lines.
Yep.
And yes, I use this in my research a lot. Can you click once more?
Okay.
So I use this in my research a lot where I have, you know, an optimization function or an objective function where I'm trying to minimize the error between my measured data and my simulated data. And, you know, you run the optimization algorithm to try to find those inputs that give you the result that you're looking for. And that's how you can characterize thermal mass and thermal resistance with some of the metrics you measure from the R value test. We're just really not doing the work. We have the data, but we're not using it all the time.
That's amazing. So let's get characterizing for 800.
All right. So ASTM C1046, which, as I said before, is the standard that talks a lot about R value testing, states that this much training data needs to be measured to characterize an envelope component. And we're talking about how many, if you had to guess, how many hours of data do you have to measure in order to do this?
I mean, based on what we've been learning, I guess, through your research, is that we need to take a lot of the lag into consideration. So effectively, there needs to be enough time to establish the effect on the lag on you know, the building performance. So yeah, Rahab's saying like minimum 72 hours, and I kind of agree. Like it needs a minimum of like a couple of days, I guess, just to be able to effectively establish the effect of the lag. And you know, yeah, I'm gonna go with Rahab's 72 hours.
All right, let's see what ASTM C1046 tells us. So this standard tells us that characterization requires obtaining data over a long period, maybe several days, and it depends on the type of building component. And
several days. Changes. That's very inaccurate for an ASTM standard.
Yeah, I was pretty surprised by this too. I thought that a standard would be a little bit more specific about that, but turns out they just say you need a lot of data. And you need to leave your equipment outside for a while.
Well, I'm going to take Rahab's answer as my standard, 72 hours. That's it. Yeah, she's doing a better job.
Good estimation.
Yeah, that's definitely a good estimation. And actually, let's do it for 1,000. Let's get characterizing and wrap this up. Okay, you're welcome, Rahab.
All right. So researchers from Georgia Tech, i.e. myself and my advisor, Tara Crawford, found that this many hours of data should be measured to characterize an envelope component. And once again, we're trying to tackle the same problem, but maybe put a more specific number on there.
Okay.
So we know that Rahab believes 72 hours is a good way to start.
And I just said I'm going to take Rahab as my standard, so I'm going to stick with her 72 hours. But that's definitely very interesting research if you're iterating on what the standard has some deficiencies on. Anyone else for the last question wanna take it? Let's give it like 5 seconds.
Yeah, absolutely. Any guess? I mean, any number is a good number.
Yeah. Well, I guess no one wants to go over how 72 hours.
Now, but it's all fine.
All right.
Oh, okay. 120.
Wow. Okay.
Total hours of a year. That would be a very accurate characterization. I'll tell you that one.
Okay.
It may be a little more data than you need.
Yeah. 120 hours and 72 actually are right on the spot, I guess,
Yeah,
could be enough to
we're
establish.
starting to say a few days. All right, let's see the answer. So can you click once more?
Yep.
Working through my research and fitting a lot of typical building envelope components in a lot of envelope assemblies, and fitting all of the walls in the ASHRAE database from ASHRAE fundamentals, I calculated that you need about 47.8 hours, so maybe about 49 hours worth of measurement data to fit the or to understand the thermal properties of typical building envelopes. You may miss some of the really high mass ones, like if we're talking about, tilt up walls, like in a big box store or something. But for the most part, 95% of them, you should be able to characterize with about 2 days worth of data, give or take.
Wow. Okay. Well, that's definitely very useful, because you don't want to be taking data more than you need at the same time to get that kind of thing.
You really, as a contractor or somebody doing this out in the field, you don't want to leave your equipment out in the rain and the sun longer than you need to. So 48.
So actually, we got someone that's a 48. Go Joe. Go Joe. So
yeah, Joe knows what he's talking about. Maybe Joe read my paper.
Well, yeah, it really seems like a paper worth reading. So I guess at the end of this, I guess the winner of this actual Jeopardy HPBL IBPSA-USA, very long name, webinar edition is actually IBPSA-USA. It's actually all of us. I think this is very useful research that you've showed us today, Tyler.
And likewise for your research, yes, sir. I mean, we're all winners because we learned a lot here. We learned a lot about envelopes and why we need to think about them. And
the other thing is, really, we hope everyone here learned a couple of really interesting facts, statistics, the importance. Okay, thank you, Jonathan. We had a lot of fun. Thank you for everyone that actually helped us out on these answers, because really this is how we do the thought process. I today learned a lot about Tyler's own research, and I guess he learned a lot about mine. I guess, but we really hope everyone learned something in a very fun way, and really wanted full-on activity. But thank you for making this the reality. So now it's time for even more questions. So if you guys have any questions, please go ahead.
All right, thanks, Tyler and Yasser. That was really great. You asked us a lot of great questions.
Yes,
I'm hoping that now we'll ask you a bunch of great questions. Everyone, if you have questions, please type them into the chat, and we'll hope to get through as many as we can. I want to remind everyone right now, for AIA credit for this, please email your AIA membership number to info@aiaeb.org. While I'm giving everyone a minute to put their questions into the chat, I want to start by asking one of my own. So you mentioned that how much of ASHRAE standard P211 we can get from non-destructive testing. What I'm wondering is, are there important characteristics that are missing from that standard? And based on what you've looked into in non-destructive testing, are there other things that we could be adding into that standard?
That's definitely a great question, Nathaniel. So standard 211P is for commercial buildings. It's very generally written as any kind of standard. It doesn't really go that much into a lot of details. It just kind of we kind of found it to be more of a general guideline towards looking at different factors. But it really doesn't go in depth into what exactly do you need to be, looking for in depth, and specifically the aspects that have to do with anything that has to do a time lag. So really what needs to be going into there is that you're just looking in general at a very high level way at the standard itself. When you at the building, when you're going through the standard, what we think the improvements can be is that effectively to be more specific in certain points and saying you need to do this and that, and at the same time is to look at NDT data over time. So and another research that we've established at the HPBL with Dr. Tariq Braka and Dr. Kaiwan Chen is that we've looked at thermal envelopes over time in a time-lapse thermography kind of way, and we were able to identify that when you're measuring, for example, certain aspects of performance, they're not the same at the same time. And when you look at it through a longer period of time, you can really, the numbers are going to change a lot. Standard 211P doesn't really go into this a lot, and I think it definitely is important to note these things, because if someone is not taking the time differences into consideration when you're auditing a building, you're really not going to be able. You're only surveying moment in time and not really the actual general performance of an envelope.
Okay. Tyler, do you want to add anything?
Not too much, because frankly, I don't work too much with 211P. My research is really pinpointed on thermal properties.
Okay.
But I will say, the more we think about thermal lag and thermal capacitance, the better the entire field will be as we try to talk about peak demand and so forth.
Okay, so well, Tyler, maybe this one will be for you. I saw a question coming in from Scott. Scott, do you want to unmute and ask your question? Scott, are you with us?
Yeah.
Can you hear me?
Yep.
Yes.
Great. I had to replug in my mic. Yeah, I'm wondering about the utility of these non-destructive techniques and when is the best use situation for them. In Denver, they're trying to clamp down on how effective your models are. They want them to be really accurate in the future. They got a timeline laid out, and after a certain number of years, you really need to peg your results with your early efficiency model for new buildings we're talking about. So I'm wondering, we're talking about existing buildings though, strictly. Yeah. And, is it used for, say, do we want to do a renovation and do a lot of efficiency upgrades? I'm not sure that that's going to be a lot more worthwhile than looking at energy bills, comparing those to baselines. And, it's a lot to go through to do all these non-destructive techniques, and certainly can accurately characterize the existing building that way. But once you get those results, what's the best use for them?
Okay, Scott, that's definitely a great question.
Yeah, I think we can both attack that one.
Yes, so I'm going to attack it first from my perspective, and Tyler, please go ahead, because this is really at the heart of our research. I think, Scott, you really right on it. I'll say this. Effectively through our research as well, you said when you're looking at baseline models and different stuff and just comparing bills. When we're talking about even simulating to a baseline model or just comparing certain data when you want to, like, for example, put in a retrofit or as such, what we are trying to do is we are trying to make even the models that, if you want to simulate them, be way more accurate than they generally be. Like when you're running things like Energy Plus, depending on what algorithm you're, for example, using, some of the algorithms, the simpler ones, like the conduction transfer function, doesn't really have variable thermal conductivity. It's really for example, a fixed number that goes in and you run with it. There are more advanced ones, but there's a lot more inputs that have to go through with that, and you need to know a lot about your materials to be able to kind of calibrate and kind of squeeze the best way out of it. Through our research, first of all, the use for NDTs is that without having to know that much about everything in there, let's say you're doing, and we established this, we said a lot of these buildings are built pre-1970, pre-1980. A lot of that information in there isn't really available unless you want to get a drill and know what's inside that building. You want to measure it at different spaces to be able to do a effective retrofit. Really what we're saying is that these are tools that you can use to start understanding everything needed about the envelope, and in a time-lapse manner, not just as a single point in time. Look at it at different times and start establishing. So this is what Tyler showed, kind of you need this many hours to start calibrating and knowing exactly where it's going to be. When there's any kind of lack of information, both when you want to put it into the model and you want to know about your building, entities can do wonders in just kind of extracting all that info out. And what we're trying to do, at least in my own research, is give the reader a way to be able to just identify, I'm going to need this, and that to extract this, and this information. And that's kind of it from my side. Tyler, if you want to tackle that as well.
Yeah. So if we're talking about new buildings, one of the biggest motivations that I work with in all of my thermal modeling research is, if you design something, it is very, very, very rarely ever going to be built the way that you design it. You often have no idea how your wall or roof assembly actually comes together because you weren't sitting there watching everybody install it in the field. Maybe you were, but if you have all the time to do that, then good for you. You will have an efficient building. But oftentimes when we actually install things and when we actually, build them, we build things and we model them in completely different ways. We have absolutely no idea about if things are performing the way that we actually believe they are. And that's really important. And that's why I'm trying to, advocate for working with all of these existing techniques that we have for R-value testing and try to, interrogate the data a little bit more and pull stuff out of that. Because if you interrogate that data a good bit, then you can pull out effective thermal resistance and effective thermal capacitance so that you can actually take those inputs and put them straight into your energy model to see the difference between your baseline and what you actually have whenever you're, retroactively coming back and looking at your building years from now. It's also useful if we're talking about retrofits, but of course, retrofits are a clear candidate here, but new buildings, it's also important to really look at those because not everything comes together the way you think it does.
Yeah, maybe especially if you're required to have an accurate model and it turns out to be not accurate. You went back and you substituted the as-built into your model. It was still not accurate.
Yep.
Yeah.
That might be a best use for it, but that would be for new buildings.
Yeah, absolutely. And specifically in my research, that would definitely be what I would say is that you need to look at is, drop those new parameters in after you run some of the tests and see what the difference is, see what the discrepancy is, and see if you're any closer to where you thought you'd be.
So is that in lieu of or after substituting as built into your model compared to as designed?
My main goal is to really break up this discrepancy compared to your as-built model and your design model. So I think that it's just really important that we integrate all of these workflows and all of these NDT techniques into retroactively looking back at our building.
All right, thanks for that question, Scott. We've got a couple of questions that have come in from our YouTube listeners. So I'm going to sort of combine a couple of questions from Joe and Nelson. Can you talk about what equipment is required for these tests and about the cost of that? So, if you were, say, going to characterize a space for 48 hours, what would be the cost of that testing?
Yeah, I can definitely speak to that from my specific research. So the equipment itself, to be honest, it does not have to be anywhere near as expensive as it is. Typical R-value testing kits cost a few $1,000s, and they use sensors that, to be honest, are not that expensive. It's often that you're paying for the whole package for somebody to put it all together for you and run all of the algorithms so that you don't have to worry about it. So it's a typical R-value test cost. For my estimation, I believe that they cost like $5,000, something like that. That's what I've seen. But that's just, in my local area. I don't really know, globally and, countrywide how much these things cost. But the equipment itself does not have to be that expensive. A simple thermistor that you could use to measure temperature costs like $1.50 each. And then the heat flux transducers, you could buy those for like as little as $50. So the equipment is not the worst part. The worst part is the labor in having someone else design all these algorithms for you, which I'm trying to tackle with my research so that I can get these methodologies out there and make them a little bit more accessible for people.
Yasser, do you want to add anything to that?
Yeah, so I was just going to say, I think the 48 hours was specifically targeting to Tyler, but I would say one thing. Definitely these techniques can range in price. The equipment to conducting these entities can definitely range in price. Some are in a couple $100s, some are definitely in the thousands. But one great characteristics about non-destructive testing is the replicability. This is something that maybe it's kind of an investment. When someone uses it, you can replicate it as much as possible. Different buildings, different envelopes. And I'm not here to endorse any company and say like this product's better than that or such. But there are many. There's a lot out there, and a lot of it has has become industry standard in a way. And the industry standard stuff always keeps getting cheaper and cheaper over time. So effectively, all I'm just trying to say is an investment in an NDT is definitely something that you can always replicate. And it's part of the properties of NDTs that made us want to look into them. And, you know, even us at the HPBL, we keep trying to get new equipment and apply it through different for different research. So in the same kind of sense, when, you know, if you do acquire some sort of non-destructive testing equipment, you could definitely replicate it on many different buildings. So it is a good investment, even if it's as I said, sometimes a bit more expensive, but depending on what you're looking at.
All right, thanks. Here's another one coming in from YouTube from Joe, asking about power sources. So I imagine that on job sites, there might be unreliable power sources. What are the needs there in terms of setting up one of these tests?
Yes, sir, I can go ahead and go first because mine's definitely pinpointed. So as I said before, a lot of the equipment that we're working with when we're talking about thermal characterization, it's not necessarily specialized, not necessarily expensive or power consuming, or largely power consuming equipment. So from my research, I actually built a test setup to characterize assemblies, and I have put a very, very, very small lithium ion battery into my little sensor box. And from my calculations, I can run my my test rig for about 31 days on a very tiny, like 200 watt hour battery. So my research can definitely, you know, survive a job site, and it could definitely be outside for a while. Yes, I don't know. You got a taller test, and some of these things use a lot of power.
Of course, if it's a longitudinal kind of study with time involved, it really depends on, you know, what you're using. We've seen thermography being used in kind of a time-lapse capacity as early as the 90s, through just, you know, having a fixed thermal camera looking at a particular wall for 3 days. This was specifically done in Japan by Hayano et al. And they've used effectively batteries, really what you're using, depending on the type of equipment and the type of survey you're doing. So if this is longitudinal, you're going to have to be relying on batteries. And part of my research effectively was that for each category or each part of equipment, can it be carried on drones? If you noticed when we were like kind of stating that, and in the paper where we showed that diagram, we have a category saying, you know, are you able to carry this on drones or not? Specifically, by being able to be carried on drones, you are kind of doing a replicating process, because the drone has to land, you change the batteries, and you do it again at different time steps if you're doing it in a time-based perspective. But if not, really it's just a point in time, then effectively the batteries that are built in should be more than enough to do the research.
All right, thanks, guys. Here's another question coming in from our YouTube listeners, from Kevin. Can you make a comparison to, say, thermal imaging? So I assume that that's looking at a difference between R-value testing and thermal imaging. And he's also interested about application of machine learning to that.
Yeah, that is a very fun question. This is actually a point in which my research started out. Originally, I looked at R-value testing and said, oh, we should be able to do this with thermal cameras, right? And you can. There is a significant amount of uncertainty due to just the major uncertainties and the major discrepancy between what we think convection is doing on the inside and outside surface of a building versus what it's actually doing. So technically, theoretically, you would be able to do an R-value test, or even, you know, tease out thermal capacitance with 2 thermal cameras that are set up, taking a lot of pictures over time. And if you are really good with machine learning, you may be able to build a program that extracts all those temperatures and feeds them into a model. You could definitely do that. You're just going to have major issues with convection, because it changes due to wind patterns, it changes due to temperature. It's tough. You'll just have to make some assumptions, and that's really the name of the game, is making some well-calibrated assumptions based upon what you're seeing for convection. And then one other thing that I do want to prop is that you can definitely apply machine learning to these problems. I have looked at what I'm doing now, and I'm doing a lot of inverse finite element heat transfer modeling But you don't have to go that route. If you really want to, and you really want to develop an extensive training set, and if you did a lot of tests, theoretically, you should be able to build a machine learning model to back out what the effective resistance capacitance of assemblies are. Something I'm actually using machine learning for doing is taking those effective resistances and capacitances that we measured and mapping those to assemblies so that we can try to infer what things are actually built out of after we run all these tests. But yes, sir, I mean, I think there's a lot of opportunity for machine learning in your space.
Definitely. So we actually have been using machine learning in one of our projects at the HPBL. What we're specifically using it for is to identify thermal anomalies on envelope. So we're using the infrared camera, but we're training the actual using computer vision and machine learning to actually identify the anomaly, where it is, what type of anomaly it is, whether is this a thermal bridge, is this an infiltration exfiltration issue, etc. So machine learning definitely can help show those out. In terms of finding out R value using thermal infrared imagery, there's actually a paper on one of our collaborators that we've worked on at MIT. This was from soon to be Dr. Nurhan Bayoumi and Dr. John Fernandez. They worked on a technique. This was a recently published paper where using an infrared thermal image and a bit of calculations and knowing the temperature on the inside, you're able to infer that. Now, in theory, the more you feed data into an ML algorithm that you're just cross-referencing inside temperature versus outside in this, you can start using it in a way where automatically it's going to tell you certain thermal properties of the envelope.
All right, thanks. And I think this follows right along from that. This is from Nesselhan. How can unseen deteriorations on the building envelope be detected by photogrammetry?
That is definitely a great question. So effectively, through as we surveyed in the literature, there are certain applications when you're using high enough. So are you talking about the unseen? Let me specify there. So through the research, we found applications where if there's a crack on the facade, if you're using if you're taking a close enough image, if you're taking it with a high detailed enough resolution, the photogrammetry is able to kind of model the inside of the crack itself. We have referenced this in the paper itself. It might not be the most, the best application to do it. We've seen LiDAR and laser scanning being able to model things, but it has to be topical, the crack itself. If it's completely unseen, you have to go to the families of NDTs that we've identified, which are the ones built on electromagnetic waves, which are ultra-wideband and GPR and even TWIR. Those would help you see something that is topically unseen. But if there is a topical, if it goes into the envelope, but it shows up on the front, possibly using high resolution sensors, you're able to do it through photogrammetry and at the same time LiDAR and laser scanning. It is possible.
Yeah, yes, sir. Let me build on top of that. So something that I didn't hear you talk too much about is when we say unseen. I think the best way to describe unseen, at least from my perspective, is that you are a human observer staring at a wall. You could look at a wall and you could say, "Oh, yeah, it's a brick wall. I don't really know what I'm looking at." But if you use a thermal camera, you can easily see insulation defects. You can easily see thermal bridges. You could see, water. I did a lot of this in my assessment days a while back. So you can really see a lot with thermal imagery, and you don't necessarily always need to go as detailed as the other NDTs. I mean, a thermal camera can reveal a lot about the world around you. So just, pull one out and, pay a few $100 and get one that attaches to your phone. And you can really find some defects very easily.
Okay, thanks, guys. I think that we've run through all the questions that we have. And so I want to take a minute as we close out to, first of all, thank everyone for joining this IBPSA-USA Research Committee webinar. If you enjoyed this webinar, please consider joining the IBPSA-USA Research Committee. Email research@ibpsa.us or visit the Zoom link, the link in the Zoom chat, and we'll send you more information. For everyone, especially those of you watching us on YouTube, Please like this video and subscribe to our YouTube channel. We look forward to having you come back to future webinars. And speaking of which, I want to let you all know that our next webinar is May 27th at noon Pacific time, when Andrew Corney presents Using Agile to Run Your Performance Analysis Team More Effectively, Lessons from Design Software, or Software Design, excuse me. All right, I want to thank everyone. Hope you enjoyed today's presentation. It's been very engaging, and we hope we'll see you next month.
Thank you all.
Thank you all for